All right, welcome back, guys. We're going to be looking at section 2.4 in this video, or at least half of 2.4 in this video. And so if you recall previously in 2.3, we were looking at measures of central tendency. So we looked at the mean, the median, and the mode. So that gave us an idea of where was the center of mass of the distribution, okay? And we also saw that some of those statistics did a better job of telling us where that center was. If you guys recall, the mean was more impacted by outliers than the other two statistics, okay? So anyway, today we're going to look at measures of variation, okay? I'll go over these objectives real quick. We're going to look at how to find the range of a data set. That one is pretty self-explanatory. We're going to look at how to find the variance and something called the standard deviation. And you're going to hear this throughout this course a lot, okay? Of both a population and a sample. And they're just pretty much almost the same. And then how to use something called the empirical rule, and then Chebyshev's theorem. This is Russian, by the way. He was a Russian statistician, to interpret standard deviation. And then how to estimate the sample standard deviation for grouped data. So this again is going to be similar to how we estimated the mean for data that was grouped. If you guys recall that frequency distribution in which we didn't actually know what the data was, but we knew how many data entries were within each class, and then from that we were able to estimate the mean. And then finally, how to use something called the coefficient of variation to compare variation in two different data sets, and this is very important. All right, so let's get started. First thing we're going to point out, guys, is we're going to look at these two data sets that we have right here. Okay, so they're from two different corporations that hire 10 graduates. And then these are their starting salaries in thousands of dollars. Okay, so $51,000, $48,000, $49,000, etc. Now look down here. It says both data sets have a mean of 51.5, which in thousands would be $51,500. So that's the average starting salary from both of these corporations. So that is very interesting because the data for each corporation is different, yet the mean is exactly the same, okay? And then the median is also the same. It's 51,000. And like I said, the data sets differ significantly. So what do we notice? Well, I'll point out, okay, something that I notice. You know, in both of these data sets, you see some 50s, some 60s, maybe 40s, 30s. But in Corporation A, we only really see some 40s and some 50s. But in Corporation B, we see some 30s, some 40s, some 50s, and even some 60s. And furthermore, guys, in Corporation A, the lowest starting salary appears to be $47,000, and the highest starting salary, if I'm not mistaken, appears to be $57,000. Okay, so that's a difference of $10,000. Now let's look at Corporation B. The lowest starting salary appears to be $33,000 right here, and the highest starting salary seems to be $68,000. That's a much bigger difference, okay? So there's a question that you might get asked in the homework. And the question would be, at which of these corporations would you be more willing to start, okay? If you wanted a decent salary starting off. So we would assume that the mean is a decent starting salary. So if I wanted to be more sure of starting off at a decent salary, I'd probably apply at Corporation A. because the variance, and I'll go ahead and use that word, is much less. So I'm much more likely to start out at a salary that's much closer to the mean versus at Corporation B, because the data is spread out so much more. I could end up starting out at $33,000, or I could maybe get lucky and start out with $68,000. Okay, but the probability that I start out at whatever the mean is much less likely. Okay. All right, so that's kind of what we're going to be studying today. How spread out is the data? Is a lot of the data just real close to the mean, or is the data spread out away from the mean, more spread away? Okay, and these are called, what we're going to be looking at is measures of variation. So how do we actually quantify how spread out a data set is? You know, here we can say that, yeah, clearly the data in Corporation B is more spread out than Corporation A, but we need to quantify that. Okay, we can't just say, oh yeah, you know, this distribution has more variation. Well, what does more mean? Okay, so that's what we're going to be looking at, how to actually quantify that. And the first statistic that we're going to look at, and that's used to quantify how spread out a data set, is called the range. Okay, and the range is pretty straightforward, guys. It's just like you would think. It's going to be the difference between the maximum and the minimum data value of each data set. Okay, so the range is equal to the maximum minus the minimum. So we're going to find the ranges of the two data sets above. So the maximum from the first data set, namely Corporation A, I think is 57, and then the minimum I think we determined was 47. Okay, so for Corporation A, the range is going to be the maximum value, which is 57, minus the minimum, which is 47, and that would give us a difference of 10. Now remember, this really means 10,000, okay, and this is dollars too, by the way. So the range of those starting salaries at Corporation A from that sample would be $10,000. And then guys, very similarly for Corporation B, okay. The range is going to be the maximum, which, if we look back up here, is 68,000, and the minimum is 33,000. So it's just going to be 68 minus 33, and that is 35, okay, which in thousands would be $35,000. So that's a big difference, right? So just by looking at the range in data, lots of times you can tell which data set is more spread out or has more variations. Now it is possible that the max and the min could simply be outliers, and that all the data, the rest of the data, is clustered real close to the mean. So that is a possibility. And that is one of the reasons, guys, why the range is not going to be the best statistic to actually quantify the variation of a data set. And so we're going to use this next thing, population variance and standard deviation. Now I want to point out that I go over this, how to find the variance and standard deviation for both a population, and then further down, further down for, let's see, for a sample. Okay, so I do the same thing for a sample, and guys, it's pretty much exactly the same, as you'll see. All right, so you'll see the relationship between the variance and the standard deviation. These are very, very similar. Okay, so like we saw, the range is going to be easy to calculate, but it only includes two members of the data set. When we find the variance and the standard deviation of a data set, that's going to involve or include every single data entry. okay? And consequently, this is going to be a much more accurate and telling picture of how spread out that data is. All right, so let's look at how to find it, and we'll look at some of what these Greek letters mean. So the deviation, so that word deviation, that means, when you think about the word, say, deviant, you're talking about somebody that differs from the perceived norm, okay? So that's what a deviation in a data set is. It's basically the difference from that particular value from the mean of the data set. Okay, now we're starting off talking about a population here. So these parameters, or these Greek letters that we're going to be using, these are going to denote parameters of a population. That's what a parameter is, if you guys recall. Okay, so X just represents a data entry, okay? And so the difference between the entry and the actual mean of the data set, so remember, for a population we use the Greek letter mu. So the deviation would be X minus mu, or the actual value minus the mean, okay? Oops. So that's what a deviation is. Now, we could find the deviations of all the data values from the mean, but if you were to actually do that, you would get a sum of 0, okay? And the reason is because the mean is the balancing point. If you were to graph all the data on a number line, the mean would be right in the middle. You would have just as much weight on one side as you do on the other, okay? Or in other words, mathematically, you would have just as much positive deviation as you would negative deviation. And so that's why the sum of all those deviations is always going to be 0. So then that's not going to work, okay? So in order to not get 0, if we sum up all the deviations from a data set, we end up actually squaring each deviation, and that's what this tells us right here. So to find the population variance from a population, you're going to find each deviation, that's what this means right here, X minus mu, and then you're going to square it. And the thing about this, guys, is that when you square either a positive or a negative, you get a positive. Okay, so we're not going to end up getting 0 again. So you're gonna find every single deviation, you're going to square it, and then you're going to add up all of those. And that's actually what this symbol right here means. Okay, we call this sigma. So guys, in statistics, as you've already probably observed, Greek letters are utilized a lot. Okay, so anytime you see this sigma, this is capital sigma, by the way. Oh wait, is that right? Yeah. That means the sum. Okay. No, I'm not right. No, I'm wrong about that. That's actually a different Greek letter. It may be capital sigma. I can't remember. But the thing to remember is that it represents a sum. So we'll be seeing this symbol throughout the course a lot. Okay, and remember, sum refers to addition. So what we'd be doing here is finding the deviation, squaring it, and then adding it to the next one. Okay, so typically what you do is you find all your deviations, you square all of them, and then you add them all up. And then you're going to divide that by the size of the population. So remember, we use capital N for the size of the population and lowercase n for the size of the sample. And then this letter right here, this Greek letter, which is lowercase sigma, this refers to the variance of a population, and you'll always see it squared for the variance, okay? And then to find the standard deviation, if you come down here, you simply take the square root of whatever you got for the variance. So you find the variance, and then you take the square root of it, and that would give you just sigma. And this is what's typically used, okay? This represents the population standard deviation. And the standard deviation is the best measure of the variation of a data set, or in other words, how spread out it is, okay? So if we go back up to that initial example up here, I would be willing to guess that the standard deviation for corporation B is going to be greater than the standard deviation for corporation A, simply because the data is more spread out. Now we could actually find it and quantify it, but we're not going to do that at the moment. Okay, so let's talk about the standard deviation for a second. It measures the typical amount an entry deviates from the mean. It has the same unit of measure as the data set. So if the data set represents dollars, then the standard deviation will be in dollars. Okay, it could be like, I'll just make something up. Say for corporation A, the standard deviation might be $3,000. And then for corporation B, it might be $10,000, okay? Because corporation B has more variability. And then the standard deviation is always going to be greater than or equal to 0. It's always going to be positive because of all the squaring that's occurring. And then if sigma is ever equal to 0, that means the data set has no variation and all the entries would have been the same. They would have to have been the same. Okay. And then one more thing, and we'll actually look at how to do it by hand. So as the entries get farther from the mean, or more spread out, in other words, the value of sigma is going to increase, which makes sense because those deviations are going to be bigger, and you'll be squaring them. So a large standard deviation indicates that the data is more spread out away from the mean, and a smaller standard deviation indicates that the data is closer, more clustered around the mean. All right, so if you were going to do this by hand, and guys, there is one worked out here by hand, but we are not going to do these by hand. Simply because it involves so many calculations and it's so time consuming. We have software. We're going to use our calculator, and I'll also show you how you can do this using Excel. Another thing too is that when you're doing it by hand with so many calculations, it's easy to make an error. And one error will cause your resultant standard deviation to be incorrect. Okay, so the first thing you would do if you were going to do it by hand is you'd have to find the mean. So you sum up all the values, all the data values, and you divide it by the size of the population. And then you find all the deviations. So each data entry minus the corresponding mean, or minus the mean, rather, and then you square each of those deviations, okay? And then you sum up all of those squares. That's what this means again, remember. And actually, we discussed, I didn't think about it, but we discussed this in the last lecture in 2.3. And then the sum of all of those square deviations, you divide it by the size of the population. And this is the variance right here. This step is the variance, okay? And then when you take the square root of the variance, you get the standard deviation, okay? Remember, when you take the square root of something that's squared, you get that something. All right, so let's look at how you would do it by hand. So I actually took this from another class that I teach, this data right here. So we don't know what this data represents. It could be minutes, it could be dollars, it could be feet, miles, whatever. Okay, but this is the data in any case. So this would be our x's, and let's pretend that this data represents a population, not a sample. So To find the deviations, well, first of all, you need to find the mean, which I did. If I add all these up and divide them by, how many do we have here? Let's see, 2, 4, 6, 8, I think there's 11, okay? So if I were to have added all of these up and divide by 11, I would get 7.2. So that's the average. And you can see these data values are clustered around 7.2. 7.2, it would be in the middle of this distribution. So to find the deviations, you take each data value, subtract the mean, okay? And this will tell you if you get a negative, that just means that data value is below the mean. And if you get a positive, like on these up here, that means that this data value is above the mean, okay? Now, if you were to add up all these deviations, you would get 0. That's what I was telling you earlier. But then what we do is we square these deviations, okay? So we take each of these deviations and we square them. And notice all of these are positive, okay? And then what you would do, guys, if you look back up here, you would sum up all of these squared deviations, okay? So you would find the sum of all of these squared deviations. And, you know, that sum, I'm not going to actually add up all these guys, so it's going to take way too long. You'll get a number, and then you're going to divide whatever you get by the number that's in the population. So in this case, it would be 11, okay? So I would be dividing this by 11, and that would be the variance. That would be sigma squared, okay? And then if I wanted to find the standard deviation, I would just take this whole thing, whatever number it represents, and I would take the square root of it, okay? So the variance, and then the square root of the variance is the standard deviation. Okay, and you'd get another number. It would be a smaller number. And if there's any variation in the data at all, it's going to be a positive number. Okay, all right, so that's how you would do it by hand. So guys, you know, you might want to try it with a small data set, like maybe this one, doing it by hand. But you need to make you a table, and you need to list out all these numbers, and then find the, you know, the appropriate sums, etc. Okay. What we're going to do is we're going to look at an example of another data set, and we're going to find well, it says here to find the range, mean, variance, and the standard deviation. Okay, but we're going to find the variance and the standard deviation and even the mean using the calculator. In fact, I think we'll use the calculator for all of this. Okay, so let's go ahead and input this data. Maybe I should have already had this done. So I'm going to put it in list 1 again, but I want to clear list 1. So go up there, highlight it, and hit the clear button. Remember, don't hit the delete button or you'll delete that list the way I did in the previous lecture. All right, so let's input these values. 1.4, 2,330, 2,700, or 2,700 in other words, 7,870. Remember, when you're inputting your data, guys, accuracy is crucial here, because just like if you were finding the standard deviation by hand and you make one error, if you input one value incorrectly, you'll get the wrong standard deviation. Okay, so when students tell me that they did everything right, but their answer is wrong, I typically believe it's because they erroneously input a value, okay? All right, 4,500, and then 0.09. Okay, so I've got my data in there. Hit enter. And by the way, this data represents the densities in kilograms per cubic meter of the 10 most abundant elements by weight in Earth's crust. Okay, so you have things like iron, silicon, let's see what else, probably maybe aluminum, oxygen. Anyway, oxygen would probably be this one. See, some of these values are really small and some of them are rather large because you're talking about a cubic meter. How much would a cubic meter of these different elements in the Earth's crust weigh? Well, some of them would weigh quite a lot. Yeah, anyway. Okay, so what we're going to do now, let's go back to stat, and let's come over here to calculate, if you remember. Go to one variable statistics, hit enter. I want to make sure I've got the list into which I put my data, right here, which I do. I'll go down here to calculate. Now remember, if you're using the free app, guys, the interface might look a little different, but I'm sure you can figure out what you need to do. Okay, so I hit enter. All right, so now I want you to notice that the calculator is always going to give you X bar and not mu. Just know that if this represents a population, then X bar is actually mu, okay? So we've got that, so I'm going to go ahead and say, let's let mu be, whatever it was, 2,251 point, we'll say 15. I'll round to 2 decimal places, okay? And this would be kilograms per cubic meter. Whoops. Need to cube that meter. Okay, so this would be the average density of the 10 most abundant elements in the Earth's crust. Let's go back to the calculator. The nice thing about the calculator is that it'll actually give us the minimum and it'll give us the maximum. It doesn't actually give us the range, but you guys know that one's not difficult to find, okay? So the range here is just going to be the 7,870. Remember, the maximum minus the minimum. Okay, and the minimum is 0.09. And if we do that, let's see, well, I think that we will get 7,869.91, okay, if I'm not mistaken. And again, this would be in kilograms per cubic meter, okay? All right, I think that's right. Okay, now what about the variance in the standard deviation? Okay, so because we're pretending that this is a population, the variance would be denoted this way, sigma squared. And guys, if you look here, look at, so we got X bar. It'll give us the sum of the X's. It'll give us the sum of the X squareds. This is something called the sum of the squares, or wait, there, yeah, the sum of the squares. Don't worry about this. But notice right here, or excuse me, no, I said that wrong. This is S. We'll talk about this here in a minute, but notice right here we see sigma. Sigma of X. That's the way you read this. So this just means this sigma is the standard deviation of all those X values for this particular population. And it tells us what it is right here. It is 2,264. I'm going to go ahead and write down sigma, 2,264. We'll go to 2 decimal places, 0.01. And this would be in kilograms per cubic meter, because remember the standard deviation is in the same unit as the actual data values. Now the variance, the calculator doesn't give us the variance, okay? But you can take the standard deviation and you can square it. So if I were going to do this using my calculator, I would want to use more of these digits past the decimal place just for greater accuracy. So I might say 2,264.0138, something like that. Okay, so that's actually what I'll do here. .0138, I think it was, and I'm going to square this now. I'm going to enter, and you're going to get a big number for the variance. Let's see, 25758. If we go to two decimal places again, we'll say 49, okay? Now, I want to point out the units would be squared. I'm just going to write it like this, cubic meters, and the unit would be squared, okay? So most people, you don't really use the variance much because it's not even in the same unit as the data. You always use the standard deviation. Okay, now this number would be 5,125,758 and 49 hundredths. All right, so that's how you do it using the calculator. We'll get some more practice later on. And I want to show you can also use Excel. And I've got the data already in here in Excel. So remember we saw how, you can select, I can say, okay, let's let B equal, and then I can come over here and I can find the mean if I wanted to. Make sure you have this set to statistical. Let's see. Oh, wait. Yeah, remember, it doesn't give the mean, it just gives, it has listed the average. And then you just drag over the cells that contain your data, and you enter. And so this is what we get. And notice this agrees with what we got with the calculator. I could do part C, or not part C, but I could let this cell, C1, equal the range. So come over here. Whoops. Let me try this again. Now some of these functions that you use regularly are just going to appear, okay? But I need to find the range. I'm not sure which of these it's going to be. Let's try this first one. Click OK, and select these same. Oh, wait a minute. I selected rank and not. Let's try this again. Anyway, guys, the point is you can play around with Excel. Like I said, well, range is actually not in here. It's probably in here listed under something else, but that's not a big deal because the range is easy to find by hand. But let's look for the standard deviation. So I'm going to let this cell equal the standard deviation. All right, so this one should definitely be in here. Okay, now notice it says standard deviation dot P, standard deviation dot A, and don't worry about these others. So the dot P means if this is a population, and the dot S means if it were a sample. So I'm going to go with dot P because that's the way we're treating this data, as if it's a population, okay? And then just select those same cells that contain the data, and look, this agrees with what we obtained from the calculator. And then I'll also let D1 represent the variance. And let's see if we can find it. Okay, So again, it says variance.p, variance.s, so we're pretending this is a population, and we'll do the same thing. Click OK, and we get the same values. However, notice it rounded. Now, if you widen this cell, it'll give you more accuracy there. Or, well, no, it doesn't. But well, it gives us more accuracy. That's weird. Yeah. Anyway, we pretty much get the same thing. If you guys. Well, notice the decimal place is off a little bit. This says 0.49 and this says 0.377. The reason there's a difference, a slight difference there, guys, is due to rounding error. Okay, if I wanted this to be closer to what Excel has, I would have needed to carry my standard deviation out to more decimal places before I squared it. Okay. All right, so just know that Excel is there for you as well. Anyway, so I'll just leave this 0.49 in here. But anyway, now as far as the samples, the variance and standard deviation go for a sample, it's pretty much the same thing. The only difference is we'll be using X bar instead of mu, and we'll be using a little lowercase s instead of sigma. Okay? And then the last thing that's going to be different is instead of dividing by the sample size, you would actually divide by the sample size minus 1. Okay? And the reason for that is sort of beyond the scope of this course. The last thing is that the variance, instead of being denoted with sigma squared, it'll be denoted by s squared. Okay, which makes sense because we're using lowercase s for the standard deviation. I'm just going to kind of scroll through here real quick. So everything else is going to be the same. You still find the deviations, you square them, you sum all those squares, and you divide by n minus 1. And that would give you the variance. And then for the standard deviation, you just take the square root of that. If you were going to do this on paper by hand again, you would sum up all your x's, divide by, this should actually say n minus 1. I'm going to need to change that in the notes. That's a big deal right there. So you would find the mean, which we denote as x bar for a sample, and you would find all your deviations, and then you would square all those deviations, okay? Then you would sum up all those squared deviations, and then you would divide by n minus 1. Well, I've got it down here. And that would give you the variance, and then you would take the square root of that, and that would give you the sample standard deviation, okay? So guys, just make sure that you know the difference between lowercase sigma represents a population standard deviation, and little lowercase s represents the standard deviation for a sample. Okay. I think this might be a good stopping point. We'll pick back up in part 2, finding the variance and standard deviation of this sample. Okay, so this is not a population, but rather a sample. Okay, so we'll kind of refresh using the calculator and maybe using Excel again, although the steps are going to be the same. Okay, so I'll stop for now.